I'm not good at jokes. So let's start. So this is actually a truncation of the actual title on the paper. So this is joint work with Yang Chen, who maybe is not here because he's at his internship, Mohammed, who's off in Vancouver, myself, Andrew Patterson, who will be a PhD student joining us from Indiana in the fall, and Martha. So this is an HCI paper. Mohammed's going to present the poster. So if you guys have ideas about this work, thoughts for where it can go next, improvements to the presentation, please let us know because it'll be super useful to Mohammed. Yeah, so this is a tea time talk, and as Mike Bowling says, like 20 minutes is the worst possible length of time for a talk because you feel like it's almost 30 minutes and then you make a 30-minute talk and like, well, 30 minutes is almost an hour. So it's usually just a total disaster and you try to cover too much and too much detail. So I'm going to try to abstract away from the details here and keep it about the ideas. And I really want to get through this so we can have a discussion about the techniques that we propose in this work. So I want to start off with why we were doing this work and what were kind of the take-home messages from it. So we wanted to compare Dyna-style sample-based planning methods with experience replay. I'm going to break that down a little more as we go through, but this is just kind of the high-level laundry list of things I wanted to talk about. We want to understand the potential benefits of search control compared to simple forms of replay. So that's kind of the main idea under that bullet. And then the second part is do the same thing all over again, but do it in continuous state domains. And for those of you following the literature, like, well, wait a minute, does that mean you have a new method hidden somewhere in there? Yeah, so we do have a new method. It's a memory-based approach, stores a set of prototypes. The key thing about this method is that we can sample and update this method online incrementally without storing all the data. This is an example of something where I'm not going to get too deep in the details because I want to get to our discussion phase. So previously, there was a paper that almost had like the exact same title, and it was by Harm and Rich, and it's a really cool work. It's called A Deeper Look at Planning as Learning from Replay. So Harm and Rich in 2015 actually did a theoretical analysis to show that there's a deep equivalence between model-free methods that use replay and model-based methods similar to LSTD. So they actually made this nice characterization, and then they actually proposed a couple methods in that paper. One was called forgetful LSTD lambda for prediction problems, and then the extension of that to control was LS SARSA lambda. And so why that's interesting is because it was an improvement on LSTD for online control, because LSTD is a little bit difficult to the extent of the control setting. And it was also an improvement on linear Dyna, which is also previous work in this area because it makes use of multi-step updates through things like eligibility traces, which was not possible before. So our work is different than this because this is more of an empirical comparison of planning methods like Dyna and experience replay. And we also propose a new method that's different than forgetful LSTD and LS SARSA in that it can be used as either a sample model or a full distributional model. So just to start off, I wanted to get some terminology out of the way so that, some people call lots of things models, and I want to be clear about what I'm calling models and what I'm calling planning. So model produces a prediction of the next state and next reward given the input state and action. So it's how the environment will respond to the agent's actions. These are copied from that textbook that we all like, okay? And so we can have sample-based models, we can have expectation models, we can have distribution models of overall possible next states. In this talk, we're going to focus on sample models. And so what is planning? Planning is any computational process that takes a model as input and produces or improves a policy for interacting with the modeled environment. And again, we can do stochastic one-step updates as in Dyna, or we can do expected updates as in linear Dyna, or we can do trajectory sampling approaches. This talk is going to be mostly about Dyna, so it's mostly going to be about the things highlighted in red. And so we have a very classical picture of this. So I'm just going to build in all these things. Oops, one step too far. So Dyna is this unifying architecture where we have the typical agent interacting with the world. So the environment is on the bottom, and then usually we just have one box for the agent, but what we've done is we've kind of peered inside this box and seen what it looks like. So different from the usual RL picture, we have the agents maintaining a model, and it's maintaining a policy and value function. And so what happens is when the agent interacts with the world, it generates real experience. And that real experience is used for two different things. One is to do direct RL to update the policy or value function, and it's also used to update a model. Okay? And then every once in a while, you take your model and you say, I'm going to generate possible states and actions in my planning loop, which we call search control, to simulate a bunch of experience to get possible next states and rewards given an input state and action. And then we just treat that as if it were real experience and update our value function and policy. So I'm a big fan of this architecture. I think the title of the slide represents exactly how I feel about it. It's a compelling architecture for AI for many, many reasons. So like I said, it unifies planning and learning. It doesn't say these things are different and you have to decide when is it model-based and when is it model-free. They're the same underlying process of updating value functions with experience, whether it be real experience or hypothetical experience. It makes really smart use of computation data. A lot of times when people first hear about Dyna, it's like, well, Dyna's kind of cheating, it's doing this thing in the background, but that's not the right way to think about it. It's organizing the data it has and its computational cycles. Model-free methods, when they interact with the world, they're very lightweight. So we have often lots of extra computation time inside the time step. What do we do to make best use of that? It's very naturally parallelizable. The planning loop can easily go in the background. It's anytime planning, so anytime you stop the planning procedure, you've improved the value function a little bit. And I really like it because it has really nice extensions to non-stationarity. So there's examples in the book about, when the world changes and what do we do about that. And I really like it because it's a really great way to frame and study the exploration problem, because you can think about doing things with the rewards in the planning loop to inject curiosity and other heuristics to make you visit different parts of the space, because then your method is actually planning to get to different states for different regions that you can design in. Now, the caveat that's sitting at the bottom of the slide the whole time is, but that's kind of, all of this is true about the Dyna architecture, given that we're in a tabular environment. And so there's this other thing going on that's called experience replay, and it's really become a really key tool for training deep reinforcement learning systems. And so I don't think any of this is controversial. It's very similar to the Dyna architecture, but it's been highly successful in continuous state, as in like robotics domains, and high dimensional problems, as in Atari and visual inputs. And so experience replay is commonly combined with deep neural networks to help training. So it provides a source of mini batches to update the network, because we like to update our neural networks that way, not just sample by sample. Experience is sampled randomly from the replay buffer, so it gets us much closer to the IID setting, training setting that the algorithms like, but it's not too off policy. And of course, if you do things like prioritize too much, you make things too off policy and you get yourself into trouble. And it also nicely prevents forgetting of rare and useful experiences, which you might want to replay later. And so I really like to think about ER as like a model-based approach, where we're just using our recent training data as a type of model. And so this kind of begs the question of what are the advantages of just saying, hey, we're just going to do replay approaches versus trying to build models and see what the specific advantages of them are. And so when you think about it at a high level, I think these things are at least intuitively true to me, and this is kind of how this work started, thinking this list of things and saying, is this true? Can we show it in domains? And what kind of methods do we need to design to show if these are true? And so potentially the model could be much more compact than a replay buffer. Replay buffer could be huge. You could spend a lot of time in the world, and so we think that maybe the model could be more compact. The model could be more robust in non-stationarity. I like to think of a small change in the world that maybe results in a small change in the model, which could be revised very, very quickly. But that might result in wholesale changes to the value function and to the policy. And so, we think that making a small change to the model, and then you run your planning loop, that it could quickly update your value function, and you might get a benefit there. The model kind of by design is attempting to cover the whole environment. It's not just forgetting about things because it's been doing this one thing for a really, really long time. It's trying to keep information across the whole domain, and that should be useful as well. And of course, there's potential disadvantages of model-based approaches, and it's something that often people spend a lot of time studying, like Eric Telvidi has spent a lot of time thinking about this, which is your model could be wrong, and in fact, you don't even know it. And so this can be particularly problematic if you want to sample a next state and then use that as input to your model process and keep rolling out states along a trajectory. The model errors compound over time, and that can become really problematic because you just end up in these preposterous situations that don't correspond to reality. And so the other kind of hypothesis underlying this work is that there are additional benefits that you get when you build a model, especially when you think about what we can do with search control, the specific things we can do under search control that are only available to model-based approaches. So I've been leaving a little picture of Dyna here to kind of help you remember the parts we're talking about. So right now we're going to talk about the search control method, which is basically how you decide which states and actions to sample in your planning loop and what order to put them in and things like that. So there's a lot of subtleties in search control in Dyna. And so, like I said, it's just how states and actions are selected for the planning phase. We usually store state action. So this is classic random Dyna from the textbook. We usually store state action pairs in a queue. But there are several interesting design decisions to be made, which is, how you add things to the queue in what order, how you sample from the queue, and also how you remove things from the queue. So maybe we're in a world that's really large and we expect the queue to become very, very large because maybe we're interacting for a long period of time. We might think about how we take things out of the search control queue. So I'm going to refer to this as the search control queue, and what experience replay samples from is a buffer. So there's a bunch of different ways that we can refine search control, and all of them are discussed just in the standard textbook. And I think they were all there in the 1998 version of the textbook. So it's nothing new and fancy here. And these things have indeed been looked at in the context of experience replay as well. So of course, there's nice clear examples where you have a long episode and you've made many, many updates, but there was only a change in the value in the very last transition. And so if you randomly sample the states you've seen before, you're mostly not going to do very much work. You can mostly make 0 updates. So we can prioritize the samples in the search control queue, which just focuses on things we expect to have large updates. We can do that with a variety of methods, including based on the TD error. And we can also do things where we try to inject a little bit of randomness to cause some diversity in that process, which has been investigated with experience replay. Also, another big piece of this is predecessor states. So states that lead into a state that had a large update, a large TD error, could also be potentially states that will lead to big updates. So we might want to stuff those things in our search control queue and design our models so that process is straightforward and easy. And then finally, there's this concept of on-policy sampling, where the queue actually just controls the list of states that we've seen before, ordered in some way. And then instead of remembering the actions we've taken, we just always query what our current policy would do. And so for a while, this chapter of this section of the textbook, Chapter 8 on Dyna, went missing, and then now it's back, and I'm really happy about that because I think it's a really interesting technique. And in color now. So those are kind of some of the things we can do to kind of take advantage of search control, and you can do them to varying degrees with experience replay. And in fact, a lot of these things were talked about in Tom Schall and David Silver and work on prioritized experience replay. So kind of going back to the objectives of this work, the first time I told you about my objectives were more high level, and now I want to refine it a little bit. So we want to compare Dyna-style sample-based planning in ER, and in fact we want to see, are there benefits to explicitly building models as opposed to keeping the buffer? In particular, how does the implementation of predecessor state search work, and how does that impact the performance? I'm not going over the details of how that's implemented in both models, but we're just going to look at the two results for those kind of implementations. And does on-policy sampling improve performance across domains? So this one is definitely not straightforward to implement in an experience replay framework because there's no guarantee that we'll have that kind of setup, but we are able to do it in a straightforward fashion in the Dyna setup. And we can discuss that more afterwards. And do these conclusions extend to the continuous domains? And like I said, we'll talk briefly about the new model that we came up with, which we call REM-Dyna. So I'm going to jump right into experiments here. So the first thing we did was just take the classic Gridworld setups that were used in the prioritized sweeping experiments in the textbook. So this is just a large Gridworld with a few obstacles in it. There's a sparse reward, so you only get reward when you transition into the goal state, otherwise you get 0. It's discounted with gamma 0.95, and it's episodic. And so we experimented with deterministic and stochastic versions of this problem, and we varied the number of states just like in Just like in the classic work, we started off with a certain size and we'd grow the number of states and everything just kind of scales up. So we just want to see the performance of the different methods as the size of the grid will get bigger. And so all the methods we compared used Q-learning as the base algorithm, did 5 steps of planning, and a replay buffer or search control queue, size 1024. And again, the idea here is that as the world gets bigger, this gets smaller and smaller and smaller. So choices about like how you add things, how you prioritize, how you delete things matters more because we're restricted in the size of the buffer and queue. And so in this work, and I think we still need to do more about this, but the oldest data in the buffer queue was always deleted. I think in non-stationary domains that might not be the best idea, especially the things I talked about before, but that was the choice we ended up making. So there's a lot of graphs here, and I'm going to quickly go over them and then kind of summarize my take-home messages from them. And so the first take-home message is right at the top of the slide, which is Dyna-Q random, which is kind of classic Dyna. Yes, Joseph?
Before you show us the differences, can you tell us what was the difference in your form relation between Dyna and ER?
So can you maybe say something more about that?
So we can think of Dyna and ER as being very similar.
That's right.
So what were the differences in the way that you implemented ER and Dyna?
Right, so ER was implemented in kind of a straightforward fashion. You keep an experience buffer of the whole tuple of experience, state, action, reward, next state, and gamma. And then in Dyna, we actually did, in the deterministic case, we make a model because deterministic just for each state action, you record the state and the reward that you would get in that situation. And then in the stochastic setting, the Dyna model changes because we actually have to do counts to deal with the stochastic nature of the problem, but ER stays the same in that case.
So you implemented Dyna with an explicit table.
That's right. That's right. And then this graph is really, these sequences of graphs, so we have the deterministic setting on the top and the stochastic setting on the bottom. And as you move across, we see the number of states in the grid are increasing from around 500 all the way up to around 1400. Just like the graphs in the book, these are cumulative reward and up. So up is good, and these are number of samples, not episodes. Yes?
Did you have any forgetting in model learning?
No.
So in a sense, if you're keeping all the counts of everything, you're remembering everything. So it would be equivalent to keeping a full-size buffer of experience and sampling from every experience you ever see.
Yeah, so in this situation, we were thinking about how the search control queue with relation to the experience buffer were the same size. So those are the things we kind of fixed as equal in this experiment. But yeah, we could definitely, that's definitely another dimension. Joseph?
So one more question. When you didn't have an entry in the table, right, so if there was no data,
Yep.
would Dyna random try and sample it, or would it only sample from things that already existed? Like how did you initialize Dyna when there was no data?
Yeah, there's the classic way to deal with this.
Muhammad and Yanshin are in here, but as far as I remember, if it was a state in action you've seen already, then there has to be something in the table. And if you haven't seen a state in action, which happens less frequently based on the way we set up the search control queue, but I'm pretty sure if that happens, then it just doesn't add anything to the queue. So it has no idea what's going to happen.
Okay. So you're not making up things when you haven't seen it.
Yeah.
Not in this case. When we learn the model, like with an actual form,
Yeah.
then we make stuff up.
Cool, I'm going to move on. And so there's way too many lines in this graph. But so there's always two camps. There's always the versions of Dyna with either predecessors and, sorry, I'll start with this one. So there's random Dyna, which is just the classic random search control. And then there's prioritized Dyna, which is prioritizing the queue based on the TD error, the absolute TD error. And then there's what we call predecessors, which is what you think of as prioritized sweeping from the textbook. So it's doing prioritization in the buffer and also predecessor search. And again, we can talk afterwards about exactly how the predecessor search is implemented, but it's pretty straightforward. And then we tried to do similar variants for experience replay. So we did predecessors, which again means predecessors and prioritization. So we use the same kind of prioritization scheme as what you would do in Dyna, not exactly the prioritized scheme that was in done in the DeepMind work, but when we used predecessors, we did use the same scheme that they did, which was basically increase the priority for related samples that came in sequence. And so there's lots of things to look at in this graph, and that's the unfortunate thing with all the things I'm trying to cover, maybe foolishly. But anyway, I wanted to go through a couple conclusions about this result, which was the Dyna-Q random shows almost no benefit over conventional ER in this suite of experiments. But you notice there's a lot going on with these red and black lines, which are always variants of Dyna, either on-policy Dyna, which includes prioritization, predecessors, and on-policy sampling. And remember that Dyna predecessors is actually Dyna predecessors plus prioritization. It's just difficult to fit all that text in the labels of the graph. Weird. So I just wanted to make a few high-level conclusions about this, which was that the best performance was achieved by Dyna with predecessors and prioritization, usually across the board. Dyna with just prioritization in the search control, so no predecessors, almost always performed worse than random Dyna and almost all the variants of ER. Random ER was always the best variant of ER, which is different than the results that were shown in Schall's work, but we could definitely investigate more sophisticated prioritization schemes to kind of tease that apart. And predecessors and prioritization in ER was most useful in the stochastic domains. Again, this is not super surprising. And on-policy search control showed its strongest benefit in the stochastic domain. So we also tried to extend the study to a continuous world. So we're not doing anything fancy here. We're just moving to a continuous grid world where you have an XY position and you have to deal with that with some form of function approximation, but the basic setup is still the same. And the only thing I wanted to highlight here was basically the conclusions kind of carry over. The things that were working the best stay working. So predecessors and prioritization with Dyna was working well, and so was on-policy, but it didn't outperform the basic one. And ER random was also working extremely well. And then the other variants of ER with different schemes of prioritizing and were not working particularly well in this domain. And so what algorithm are we using here? What is REM-Dyna? How am I using it? Okay, so that's what I want to talk about for a couple more minutes, and then I want to discuss the kind of the architecture that we use to create this REM-Dyna algorithm. So replayed experience models, that's what it's called, REM. Also sounds like dreaming, which is kind of fun. So learning and planning continuous state problems. So this is a model based on collecting a set of prototypes. So we have these tuples of state action, next state, reward, and gamma. And we want to make a model that's built out of these representative prototypes. And so I'm only going to go over this quickly, but just to give you a flavor of what the model kind of feels like, to generate a hypothetical sample, which is your next state and reward given the state in action. We compute the similarity of the query state in action to all the prototypes we have, which basically corresponds to selection probabilities. And then we just stochastically sample a prototype. Okay, so we have a collection of prototypes for this state in action, which prototypes are closest to it, according to probabilities, and we sample one of them. And then, given that sample prototype, that corresponds to a distribution which we sample to get our hypothetical piece of experience. Okay, so that's how we sample the model, and then if we want to update the model, we decide we have an online streaming way to add new experience to the set of prototypes. So we can get a new sample and we can decide, are we going to add a new prototype and are we going to delete something? We have an online method for doing that. It's based on submodular maximization. And then we can adapt the sampling probabilities of the prototypes. And there's a couple of cute tricks in there that makes this much more computationally efficient than you would expect. And we'd love to talk about it after. So this is not your grandmother's usual state-to-state model. And the grandmother in this case is Rich. So Rich often talks about we want state-to-state models, agent state to agent state models. In all our continuous domain experiments, the grid world that I went over quickly and a continuous variant of river swim that we came up with, we always actually just got to observe state. But if you think about how my model works and how I will tell you the remaining pieces of how we used it, we used our REM model to generate samples of next state and reward. And then we took that next state and we tile coded it to update our value function. Okay, so there's kind of two sources of generalization happening in this, right? You have your function approximation architecture and you have your model. And really, depending on how you define agent state and MVP state, I really like to think of REM as probably best thought of as an observation to observation model. So it's generating an observation, which you then pass to your function approximator so you can update your value function. So this is maybe not the usual way of doing things. But there are other ways to use REM that gets it more back to grandma's state-to-state model, and we'll talk about that just near the end. So, super fair question if you're thinking about prototype-based methods and things that rely on kernels. Does it scale? So our domains, of course, were very few dimensional. They were continuous but small dimensional. Approaches based on Gaussian kernels, which is one of the underlying things under our method, have been shown to be useful in lowish dimensional robotics domains. So Mark Deisenroth has done a lot of work on his method that uses similar ideas, and he uses in robotics domains, but his method is not online. It's extremely computationally demanding. And so we thought we made an improvement there. And yeah, there's been some work on scaling up kernel methods to like visual inputs. So there's particular specialized kernels you can use, but I think there's very strong concern about the scalability of these prototype methods. And so we're thinking about and exploring ideas about how we could make this better. So for instance, one automatic idea you might have is to take something like an autoencoder or something else like that and use that to convert your observations into a lower dimensional state and then pass that to your REM model. And then I feel like you're more back to the state-to-state model situation. So you're using another powerful parametric architecture to construct your agent state, and then you're using this prototype-based model to project it forward. And so how do we end up here? How do we end up at REM-Dyna? So just to kind of wrap this up, this kind of happened because we were just sitting there thinking we wanted to investigate ways to do sample-based planning in RL in continuous domains, but maybe not necessarily for visual input domains, and thinking about how we should do that. And it immediately made us think about experience replay and how these two things interact and relate. And there's a lot more experiments in the paper that you can take a look at. And I think we still need to do a lot more in this area. We need to do more domains. We need to scale up domains to really push and pull at this scaling question. And also I think we need to do more work about different, more sophisticated ways to deal with prioritization, especially in stochastic domains, because that shouldn't be a surprise to anyone. But I think we did provide additional evidence to support some of our intuitions of why building explicit models is important. And really for me, the question is, where do we go from here now? We can explore extensions to learning the similarity measure. We were using Gaussians to do this for us, multidimensional Gaussians, but there are smarter approaches based on data. Like I said, we can construct the state and use that with our REM model. But really, for me, like the open question for discussion is, is using collections of prototypes still relevant in the age of deep networks, deep learning systems, very powerful, complex parametric function approximation architectures? Is it useful for representing the model? Is it useful for some combination of part of the model is based on prototypes and part of it is used for value functions? I'm not really sure, but I think it's worth something to discuss as a group. And that's all I have. Dave.
So, nice talk. There were a few papers from DeepMind on something called episodic memory. Doing deep reinforcement learning with episodic memory. And that certainly tried to at least investigate some of this discussion point. The idea was to keep like a nearest neighbor representation of, so you've got some feature representation which comes out of your neural network, and then that gets stored in some kind of nearest neighbor representation. And now when you see some new state, like your new screen of Atari, that gets encoded into some features.
Right.
And then those features get looked up in your memory, and from the memory it pulls out. In that case, it wasn't exactly a model there. They weren't storing transitions. They were storing, if I remember, they were storing the the actual like returns
Right.
following from those, and those were used to then inform the decisions that were made.
Mhm.
But there were, my recollection is, and this is all a bit, from a while back, but my recollection is that their aim was specifically to see whether a combination of like this sort of parametric and non-parametric could do better than either alone. And
Right.
And the answers seem to be like it has a benefit for kind of fast learning. That's the idea.
I see.
You can kind of there's something which you see something once, and then you get like this one-shot kind of generalization from something like this, which is and the argument is it's hard to get that kind of one-shot generalization out of a slower kind of parametric learning.
Right.
But I don't know if they did it with this. I think it's different to try and do it more explicitly storing a model in that way.
We actually found the same thing for this experiment, because you learn a model with a neural network, and we also compared to that, and eventually it caught up, but it learned so slow in the beginning that it just wasn't as good as ER. There's an actual question though, do we need our models to learn fast, or are we imagining our models can learn slow, and then later we're going to benefit from them somehow?
So Alan, I'd like to know what kind of prioritization are you using? So are you using a TD arrow or normalized TD arrow?
Should be the absolute TD error.
So I think in that case, for this environment, TD arrow will perform worse than randomly choosing state action pairs, because if you use TD arrow as your
Priority.
Yeah. So if you use TD arrow to choose the state action pair, so basically what you will choose first is the one that near the goal state, and even though you can't make sure that that state's value to be accurate enough, and again you will choose it again. But if you choose it randomly, you basically choose all the state action pairs in the map. And we know that the policy can be optimal or can be very good, even if the value function is not optimal. So in that case, you can learn the good policy, even if you don't know the optimal value function. So I think that really depends on the task that you are doing.
Yeah, definitely. So these experiments were set up to kind of replicate the prioritized sweeping experiments in the textbook, where we had that sparse reward at the end, and picking up those samples in the middle trajectory just gave you absolutely no updates whatsoever. And so it's the same kind of idea that, and of course there's a balance between those two things, right? And that's exactly what they explored in the prioritized, I think it's called prioritized replay paper from DeepMind. That you've got this diversity problem where you don't want to just, especially maybe it's more severe in a neural network where the learning is slower, where you keep picking the same thing over and over and over. I think in these linear architectures the update happens really quickly, and so you don't spend too much time. But it's definitely true that prioritization works really, really well, and the results show this with predecessors, right? So adding those predecessor states based on the ones that have high TDR by far work the best.
Plus, it's not just picking priorities, deterministically highest priority. It's sampling according to priorities, like they do in the prioritization.
Right.
Because that works way better. Just picking according to priorities is bad.
Janie?
Also about prioritization
Mm-hmm.
based on TDR. I think you can justify it for deterministic environment. I didn't see how you can justify it with automation in the bias that we will introduce for stochastic environment. Because, do you see what I mean? Because your Bellman error is 0, but the TD error would never be 0. So even if you have the real value function, this would be saying you are picking those transitions, you are altering the probability of the transition. So you look at the outcome and of your experiment and give that as a training example to your net.
Yeah, so like I said, in stochastic domains and with function approximation, you need to use smarter forms of prioritization, and that's just something that we didn't focus on, or we didn't get to in this work, but that's something we're looking at now. Yep.
There's one more problem. So I think you were doing a linear function approximation for value function.
That's right.
Yeah. So in that case, if we do a search control, like we do it randomly, basically we lose the convergence guarantee. Like for the state distribution doesn't match with the on-policy state distribution. So in tabular case is not the problem, but in function approximation, that's the problem.
Could be. I mean, yeah, I don't know what we can say about convergence guarantees in the function approximation setting anyway when we combine all these pieces, but it's a good point.
Another way to say it is that convergence guarantees from on-policy RL come from the fact that each time you enter into a state, you also leave it. And that's kind of the property that means that you're kind of updating everything as much as everything gets updated as much as it's used. And that means that you get these convergence properties. And if you shift the distribution of the states, you might lose that property. I think that's the point. Which is true.
I think your point's true. Also, Q-learning with linear function approximation doesn't really have good convergence guarantees either.
That's also true.
Yeah.
I don't know if we're just going to stop that.
Oh, yeah. we should stop now, actually. Thank you very much, Ed.
Thank you.